All right, we're going to talk about triangles and how, so up until now, we've really been talking about how things work on the unit circle. Now, this is a trig class. We're going to start talking about triangles. So we've talked about this a little bit, thinking about, okay, on the unit circle, if we have our initial side and our terminal side of an angle, right, our angle T, and talking about where this terminal side would intersect the unit circle, um, that's our point, right? And we've kind of been defining cosine as the x coordinate of that point and y as and sine of t as the y value of the coordinate of that point, right? So we can make a triangle. We've kind of already been doing this a little bit, right? Here's our x, here's our y. We have hypotenuse length 1, okay? So what if we just take it out of a unit circle altogether and have a triangle, right? So now our hypotenuse could be any length, right? Not just length 1, but this could just be any random triangle. And we use just the relationship. This is probably how you've learned trig functions in the past, right? Not using it on the unit circle, but in context of triangles. And you would say sine of this angle t is opposite over hypotenuse. Cosine of this angle is adjacent over hypotenuse. And tangent is opposite over adjacent, right? So that's where we get the SOHCAHTOA, right? So if we're not in the unit circle, we just have a right triangle here. We can just use those ratios to find the different trig functions. Okay, so let's just practice. What if we have this angle here, alpha, and we want to find cosine of alpha? Okay, well, cosine is going to be adjacent over hypotenuse, which in this case will just be 15 over 7. Okay. All right, so an important thing to do, to understand, is that which side is opposite and adjacent depends entirely on which angle we're talking about, right? So of course, we're always talking about right triangles. All of these trig functions, we only use right triangles for. Or they only work for right triangles. So here, if we're talking about angle alpha, then this side is opposite alpha, and this side is adjacent, right? However, if we're talking about beta, angle beta here, this side is opposite, and this side is adjacent, right? So there's nothing inherent to a side that makes it adjacent or opposite. It's all in relation to whichever angle we're talking about in the triangle. And that doesn't matter if the triangle is rotated or, whatever, however it is. We can think about it just in relationship to this angle here. This is the opposite angle to it, and this is the adjacent to alpha. And for beta, here's opposite, here's adjacent, right? All right, so what if we have this triangle? It's a 3, 4, 5 triangle, and here's our alpha. And they want us to find sine, cosine, tangent, secant, cosecant, and cotangent of alpha. Okay, maybe give that a try, and then maybe pause the video, and then here we go. Sine of alpha, I have to move me over here for a minute. Sine of alpha is opposite over hypotenuse. Cosine is adjacent over hypotenuse. Tangent is opposite over adjacent. And now I do not remember what these are, right? I just think secant is 1 over cosine, right? Remember, we learned all those relationships, those identities in the last section. So cosine is just going to be 1 over cosine, so it's hypotenuse over adjacent, or 5 over 3. Cosecant, remember, is 1 over sine, so hypotenuse over opposite, so that's going to be 5 over 4. And tangent is 1 over cotangent, so adjacent over opposite, or 3 over 4. Right? So I just personally just remember these top 3 and then figure out these bottom 3 in relationship to sine, cosine, and tangent. Oops. Okay, so I'll move me back over here. All right, so we talked about, at least in class, with these special triangles, if we have a 30, 60, 90, right? So here's 30 degrees, this is 60 degrees, this is 90, or 45, 45, 90, right? Pi fourths is 45 degrees. The relationship of the side lengths to each other, we said, okay, if this is a unit circle, we know that this is just 1, and then this would be, that makes S 1/2. This would be 1/2, and this would be square root of 3 over 2. And if this was 1, that means S would be 1 over square root of 2. This ends up being square root of 2 over 2, and this ends up being square root of 2 over 2. Okay? So, given that, find the exact values of the trig functions of pi thirds using side lengths. Okay, so hopefully at this point, you are starting to memorize these trig values anyway. Okay, you don't have to go back to this, this triangle here to determine what those side lengths would be. Okay, you already know because you're trying to memorize sine and cosine of pi thirds. Okay, sine of pi thirds, if you think on your table, is, or you could think of the triangle, sine of pi thirds, or 60 degrees, is opposite over hypotenuse, so that's square root of 3s over 2s. It's square root of 3 over 2. Notice that it doesn't matter what s is, right? If our triangle is really big, really small, sine of pi thirds is square root of 3 over 2. Cosine is 1/2. Tangent is going to be the opposite over adjacent. So if we go back here, tangent of pi thirds is opposite over adjacent, which will just be square root of 3 over 2, square root of 3. Notice we also can say tangent is sine over cosine, right? It's this value divided by this value, which is just square root of 3. So if you just know these two values from your table, you're good, because now we have secant, cosecant, cotangent. Remember, this is just 1 over cosine, so 2. This is just 1 over sine. So we do the rationalize the denominator. We get 2 times square root of 3 over 3. And cotangent is 1 over square root of 3. Rationalize the denominator to get square root of 3 over 3. Okay, so if you just know these two values, you can figure out all the rest of these. If it makes more sense for you to think about these ratios, you can do that. To me, I just like to remember these two values, and from that I can derive all the rest. Okay. All right, so let's talk about cofunctions. All right. Let's look at this triangle here. Here's 60 degrees, here's 30 degrees. Notice, so sine of pi thirds is opposite over hypotenuse. Cosine of pi sixth is adjacent over hypotenuse. Notice that both of those opposite, for this angle, it's this value over hypotenuse. For this angle, it's this over hypotenuse. They're the same thing. They both are square root of 3 over 2. You've noticed this pattern on our table, right, that you're memorizing. We can see that the values are the same as for sine and cosine as we go from opposite ends, right? Okay. And it goes the other way too. Sine of pi sixth is opposite over adjacent. This value over this. Cosine of pi thirds is this value over this, right? So this means these two functions, sine and cosine, right? Sine, cosine, co is in front. They are co-functions of each other. Okay. This works with any two angles. Doesn't have to be special to pi thirds and pi sixths, right? Whatever alpha and beta are, sine of alpha is going to be this over this, and cosine of beta is this over this, right? Sine of beta is opposite over hypotenuse. Cosine of beta cosine of alpha is this over this, right? For any two angles, this works for sine and cosine. Okay, they are co-functions of each other. And in fact, let's think about how are alpha and beta related, no matter what they are. Well, in terms of degrees, let's think in degrees first. We know triangle sum theorem, together these equal 180, right? This angle is 90 degrees, so together these equal 90. So if this is, whatever alpha is, beta is 90 minus alpha, right? Because together these add up to 90 degrees. If we do it in terms of radians, same concept. This is pi halves, right? 90 degrees is pi halves. So alpha, if we have alpha here, beta is going to be pi halves minus alpha. Okay. All right, so let's think about this. Here's this table, cofunction identities. Here's cosine and sine. Okay, they are cofunctions of each other. Cosine is the same as sine of pi halves minus t, right? And here we're using t instead of alpha, right? This could be alpha. Sine is cosine of pi halves minus t. Okay, so notice these cofunctions is always pi halves minus whatever the angle is, right? Because these two angles in a right triangle always add up to pi halves or 90 degrees. Okay. So what are cofunctions? Sine and cosine, tangent and cotangent, secant and cosecant. It's in the names of the functions, right? Sine, cosine, tangent, cotangent, secant, cosecant. Okay, that's how they are related to each other. Okay, secant is equal to cosecant of pi halves minus t. Cosecant is equal to secant pi halves minus t. Okay, it goes both directions. Okay, so this isn't like 6 completely different things in a table. This is a relationship, right? But it's always pi halves minus t because that's what these angles always add up to. And this comes from the ratios, okay? Here's the kind of problem you could use this for. So here's my personal thing. I never quite understand why this is super interesting or important. I mean, yes, it's important to recognize this relationship, but this is like a minor thing, okay? All right, so if you knew that sine of t was 5/12, find cosine of pi halves minus t. Well, they're cofunctions, right? So if sine of t is this, cosine of pi halves minus that t value, we don't know what t is, but we know it's going to be the same thing, okay? All right, so now we can solve some triangles, right? These are probably the kind of application problems that you have seen before, solving for values in a triangle. If we know an angle and we know a side, we can use our trig functions to find the other sides. So we could say, okay, well, tangent of 30 degrees is opposite over adjacent, 7 over a. We can solve for a, right? Multiply both sides by a, divide by tangent of 30, and we can either know the value of tangent of 30 from our table. We could put this in our calculator, and we find that side length a is 12.1. Yeah, that looks reasonable. All right, how about for c? We can say sine of 30 degrees equals opposite over hypotenuse, so 7 over c. Again, we solve for c, multiply by c, divide by sine of 30. Put this in our calculator. It's about 14. Yeah, that makes sense. That seems reasonable. Right? All right, so we can actually use this to solve applied problems, and people actually do this. This isn't one of these really contrived things from math class. People actually use these trig ratios to find for how tall, like a mountain is, right? You're not going to be able to like get out a tape measure and measure a mountain, but you can measure angles, right? So here's the terminology you need to know. Angle of depression would be the angle from the top of some tower or mountain or tree or flagpole, right, down to the ground. And the angle of elevation would be the angle from somebody standing here looking up or measuring with a little angle tool. This is the angle of elevation. This is the angle of depression, okay? And assuming this is a right triangle. Okay, so here's an applied problem. To find the height of a tree, a person who walks to a point 30 feet away from the base of the tree, and she measures an angle of 57 degrees from the line of sight to the top of the tree and the ground, right? Find the height of the tree. Okay, well, this is just a triangle, right? This is 57 degrees. We want to know this value. So we're going to use tangent, right? Tangent of 57 degrees is going to be our unknown value divided by 30, opposite over adjacent. Our unknown value we can call height. So tangent of 57 is h, height over 30. We solve for h multiplied by 30. Put this in our calculator, and there we go. Okay, there's our value. All right. So that's the one application that we can use right triangles to solve for actual things if they're too big to measure. All right.